In order to calculate an equilibrium constant, you have to know the concentrations of each of your chemicals at equilibrium. Well, how do you experimentally do that? They can be measured in different ways depending on the reaction. When a system reaches equilibrium, the color, pH, or pressure of one of the chemicals can be measured just like we did when determining reaction rates. The concentrations of the other chemicals can be determined using stoichiometry and a trick known as an ice table. Here's an example. If you take an iron 3+ and a thiocyanate ion, it produces another ion that is red in color. You can measure the intensity of this color using a spectrophotometer. If the initial concentrations of the iron and the thiocyanate are both 1 mole per liter, and the spectrophotometer tells you that the iron thiocyanate ion at equilibrium is 0.62 moles per liter, you can calculate the other concentrations by using an ice table. ICE stands for the initial concentration, the change in concentration, and the concentration of your chemicals at equilibrium. Let's plug in what we know. Both of these are initially 1 mole per liter. In the question, we're not given any information about the initial concentration of this. We then assume that none of this was mixed into the system, so it will have a concentration of 0 moles per liter. We're also told that at equilibrium, the iron thiocyanate ion has a concentration of 0.62 moles per liter. All we need now is to complete the ice table using stoichiometry. Because we have the initial concentrations and one of the concentrations at equilibrium, we can figure out how each chemical changed. If I started at 0 moles per liter and ended at 0.62 moles per liter, that means my change was a plus 0.62. Now to move from one chemical to another, you need to times by a mole ratio. In this case, I have a 1 to 1 mole ratio. But I'm also moving across the arrow. When you do that, you flip the sign. The reason is because for every one of these that gets made, you will use a thiocyanate ion. That gives me an equilibrium concentration of 0.38. I get that by adding down in my column. To go from here to here, I have another 1 to 1 mole ratio, so this will also decrease by 0.62 and give me a final concentration of 0.38 moles per liter. Now that I have my 3 concentrations, I'll write my equilibrium expression. It is the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. If I sub in, my Kc equals 4.3. Now because this value is so close to equaling 1, then my system has roughly the same amount of products and reactants. But because it is slightly over 1, it means that my forward reaction is very slightly more favored than my reverse. Now, the equilibrium constants for many reactions can be looked up. You have a table at the back of your textbook in Appendix B. How can we determine the concentrations of chemicals at equilibrium if we have an accepted equilibrium constant? We solve this by defining one of the concentrations as x, and then solve for it using algebra. This sometimes involves solving quadratic equations. There are a couple of tricks that you can use to simplify the math and avoid doing a quadratic formula. Let's look at example 1 here. If we mix 1 mole of CO and 1 mole of water in a 2.5 liter container, studies show that the Kc for this reaction equals 8.3. Now it tells us that that occurs at 700 Kelvin. We don't have to do anything with the 700 Kelvin. It just means that we can only use 8.3 if our conditions are at 700 K. We need to find the equilibrium concentrations of each of these chemicals. Let's start off by doing an ice table. Now I have to calculate the concentrations for my initial because I have a 2.5 liter container. I'm going to take 1 mole of CO and divide by 2.5 using my equation from grade 11, C equals N over V. That gives me an initial concentration of 0.4. The same occurs for the water. Now, because the question doesn't mention mixing in any hydrogen or CO2, I'm going to assume they both start off as 0. I need to find these 4 concentrations in order to provide an answer to the question. Let's define the concentration of one of those chemicals at equilibrium to be X. Now it's easier to pick one of the products because they start off at being 0. If I do that, then my change for hydrogen will be X. Because I start at 0, I end at X, I have a plus X. I have a 1-to-1 ratio to go into CO2. Its equilibrium concentration will also be X. I have a 1-to-1 mole ratio to go to water, but because it's a chemical on the opposite side of the arrow, it will go down by X. So that gives me an equilibrium concentration of 0.4 minus X. The same is true for my carbon monoxide. Now let's write our equilibrium expression. It's going to be the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. And my question tells me that that equals 8.3. Let's sub in our values from the ice table. Now I need to solve for X. Looking at this question, I could expand out my brackets in my denominator using distributive law, and then I would get an x squared and x and a number value, and I could solve it using quadratic formula. But one trick that you can use is look for perfect squares. This simplifies to x squared over this bracket squared, because I have the same bracket times itself. Because both terms on the left side are squared, I can take the square root of both sides and avoid having to do a quadratic question. The square root of 8.3 is 2.88. I would then take my bracket in the denominator and times both sides by it so that it comes up here on the opposite side in the numerator. In order to get rid of the brackets, I would expand my 2.88 over the bracket using distributive law. I'm going to move all of my x's to the left side of the arrow. I will have to add 2.88x to both sides. Then I solve for x by dividing both sides by 3.88. That makes x a 0.30 mole per liter concentration. I then can take that value and sub it back into my ice table. The concentration of my hydrogen and my CO2 at equilibrium is defined as being x. The concentration of my CO and my water is defined as being 0.4 minus x. So 0.4 minus 0.3 equals 0.1. So by looking up a constant and knowing the initial concentrations, you can calculate all of the concentrations at equilibrium for your system. I would like you to try out example 2. One suggestion I would make before you start is to consider defining the concentration of HI at equilibrium 2x. This will make your ice table math a lot easier. You'll see why when you move from chemical to chemical.